Eusebius McKaiser on 702.
Your number one news and talk station.
I love how popular the naked scientist is. You think you can take for granted that you know that there will be the naked scientist unless I tell otherwise. And then at 9 o'clock this morning, I did not say. And coming up at 10 o'clock, as usual, the naked scientist. And a couple of people tweet and say, oh no, is there no naked scientist? There is a naked scientist.
702 and Cape Talk.
The naked scientist.
Well, naked as it were. Hello, Chris.
Hello.
Now, today's science story that we're going to start with, I can hardly even say it. Normally, I can at least fake grammatically reading the sentences on my page, but it does sound really fascinating and ghostly. Subatomic particles that can travel unhindered at that for billions of light years.
Yeah, this is a pretty interesting paper. What scientists in Antarctica, using an appropriately named detector called the Ice Cube Observatory, have detected are neutrino particles issuing probably from about 4 billion light years away and possibly a giant black hole. Now, let me wind you back a bit. In the 1930s, scientists proposed that these particles called neutrinos must exist. They're absolutely tiny, they're subatomic. They are massless, they don't weigh anything, and they travel at nearly the speed of light. They're also uncharged. And what this means is that they can travel through space across time at blazingly fast speeds, and they don't interact with anything. That means that they're unhindered and unfettered in their passage through space by other stuff, like gas and dust. In fact, there are probably trillions of neutrinos whipping through every single one of us every day. So how do you detect them then? Well, that's where the Ice Cube Observatory comes in. And what this group did a number of years ago is that they drilled holes which are nearly 3 kilometres deep in the ice in Antarctica. And this pattern of 86 holes, which are nearly 3 kilometres deep, have dangling down them cables. And these cables are arranged in a hexagonal pattern, and they have detectors on them for light. Now, when neutrino particles come streaming in from space and they pass through the nice clear ice of Antarctica where these detectors are, occasionally, very, very occasionally, they interact with a particle in the ice, and that interaction gives a brief flash of light. And these detectors can therefore plot what the direction of the flash of light is, and therefore infer from that the trajectory of the incoming particle. So that's why Ice Cube, which is built in in a cubic kilometre of ice in Antarctica, that's what its job is, to find these neutrinos. Why they're interesting is we've proposed them since the 1930s. They were first detected in the 1950s, and now we're trying to work out actually where they're coming from, because we know that the sun produces them, we know that radioactive decay produces them, but there are also very high energy particles streaming in from space. Where do they come from? What's their source? Could they open up a new vista in astronomy for us because they don't get absorbed by things and they're hard to detect? Can they tell us about distant things going on? And therefore we can understand more about how space works. And that's what this announcement this week is. They found a very powerful, energetic neutrino, some million times more energetic than anything we can make on Earth in one of our particle accelerators. It seems to have come, based on its trajectory, from a blazar, which is a structure in the universe about 4 billion light years away, where there's a very active star-forming region, where there's a supermassive black hole. And what the researchers think is that these particles are being produced when black holes get sort of cosmological indigestion. They ingest material, they burp up lots of jets of material, and that jet of material is going so fast, it then rams into itself and produces collisions that then produce these neutrinos. So this is an interesting proof of concept. It's announced this week in the journal Science by a big team, and it gives us a new insight into possibly what this structure out in deep space is doing, but also really how the universe works.
Fascinating. Bokotsi, good morning to you. Welcome to the show.
Good morning, gentlemen. My question concerns near-death experience. I have read books on this, and I was quite taken aback by the similarities that I personally experienced way back in 1965. And just wondered how true or if science has actually explored that terrain.
Okay, Chris?
Well, this is a well-trodden path. People have been speculating and investigating the science of the near-death experience for decades. And in fact, for a long time, it wasn't really subject to proper scientific scrutiny, but in recent years it has been. And scientists have done a number of experiments by doing things like putting written pieces of paper or objects in places where patients in operating theatres wouldn't be able to see them unless they did what they said they did, which was to float off the operating table when they died, look down from the ceiling of the room. Why they'd go up there when they died, don't know, but there would be objects that they could see from that vantage point but not on the operating table. When patients have incidentally reported near-death experiences and said they floated up to the ceiling of the room, the researchers have asked them, well, did you see anything? And they didn't. So this argues that they weren't really up there on the ceiling of the room. They were just having the view or the perception that they were. Now, what we think is going on when people have near-death experiences is that because you are near death or you have physically died for a short while, perhaps, for instance, you've had a cardiac arrest and so the blood flow has stopped to your brain temporarily, perhaps when this happens to you, because you're so unwell, this affects the neurochemistry of your brain. And so in the same way as when you dream, you create an alternative reality inside your head. Perhaps this state of illness, this state of hypoxia, low oxygen, creates a temporary state of sort of dreaming or alternative reality created by your brain, just like you dream. And when you then wake up, in the same way as if you're woken up in the middle of a dream, you can remember glimpses or snatches of that dream. Perhaps that's what's happening in this circumstance. But we don't think there's really any good, strong evidence for people who have near-death experiences. I mean, they're real experiences to those people, but we don't think there's anything spooky going on. We think this is a phenomenon created by the unwell nervous system.
Mike, good morning.
Morning. My question is that I don't have gutters on my house, so the rain, when it does rain, pours off. Now, in the winter, we haven't had any rain recently, but in the winter, if rain falls, it falls into open containers that I keep to water my plants. However, in the summer, the mosquitoes breed in this water. I want to ask Chris, is there something I can put into this mosquito breeding water to kill the mosquitoes, but to make the water still safe to put on my plants?
Yeah, it's a really good point. You can hear Eusebius doing his emails in the background there. Or are you checking up on me again, Eusebius?
I am indeed.
No, it's a really good point, this, because in many countries where mosquitoes spread not just malaria, but they spread other things like yellow fever, dengue, Zika virus, there are police forces and members of public health who will go around and they look for containers that mosquitoes can breed in, and they can fine people if they do this. So this is a big issue because mosquitoes, especially Aedes mosquitoes, are very good at finding pools of stagnant water, even if it's a small amount, and laying eggs in them.
Yeah.
Now, it's also very important to conserve water, and no one knows that better than the residents of Cape Town at the moment, for example. So how do we sort of satisfy those tensions? Well, one sensible approach, because believe it or not, in Britain, people have also got mosquitoes breeding in their water butts. So one thing that people are doing is being encouraged to put a fine meshwork over the access point to the bucket. So you buy some thin muslin where obviously water will go through that no problem, but mosquitoes won't. And if you can keep the mosquitoes from having access or contact with the water surface, they can't lay eggs in the water and therefore they can't breed. So my advice to you would be to put the containers there, because collecting the water is very important for judicious use of water, but keep the mosquitoes out with muslin.
Okay, thank you. Thank you very much.
Thank you, Mike. Much appreciated.
702 and Cape Talk.
The Naked Scientist.
Morris, good morning.
Good morning. Eusebius, I'd like to ask Chris, why aren't all human beings ambidextrous?
It's a lovely question, Chris.
Yeah, I'd give my right arm to be ambidextrous. Now, that's an old chestnut, isn't it?
It still works.
Do you know, I asked Chris McManus this, who literally wrote the book on this subject. Chris was Professor of Medical Education at University College London and won the Wellcome Trust Book Prize for his book Right Hand, Left Hand, and then won the Novartis Prize for the same title. It's probably the best book I've ever read on a sort of general science topic, but it explores handedness, not just of humans, but from the ground up, handedness of particles and atoms and molecules right up to us. And
wow. Is it good? Is it a good popular read?
It's a really excellent science book, Right Hand, Left Hand. I'll tweet out a link to it after the programme if anyone wants to follow us on Twitter at Naked Scientists. I'll tweet that out because it really is an exceptional book. And I asked him this a number of years ago, and he said, well, actually, the interesting thing about humans is that while we do have a dominant hand, and we don't know why we have handedness, but what we do know is that it's all to do with which side of your brain is dominant. And because one side of your brain controls the opposite side of your body, the dominant side of your brain seems to be the part of your brain where language is based. And in the vast majority of humans, 90% of us, language is in the left side of our brain. And that means the dominant hemisphere of our brain is the left side, and therefore your dominant hand that you prefer to use is your right hand. That's not to say, though, that you can't become very good at using the opposite hand. And we probably become very good at doing things with our right hand because we practice, because we prefer to use it. But actually, in people who have a disability or can't use their preferred hand, and they have to use the other hand, a friend of mine broke her arm, for example, and because she couldn't use her preferred hand, she had to learn to write because it was exam term at the university, and she had to learn to take lectures and do exams with the wrong hand. And she said, although it felt terrible to start with, she actually became quite good and could write quite neatly with the wrong hand quite quickly. And until it became okay to be left-handed, where, in 100 years ago, people with left-handedness were regarded as grossly abnormal or something wrong with them, and we used to punish these people and tie their hand behind their back and stop them using their left hand, then And in the modern era, we now know that people who are left-handed, actually, because they were forced to become quite adaptable to a right-handed world, because they were in the minority, they actually became quite good at using the wrong hand, their right hand, to do things to fit into our world. So actually, we are very, very much ambidextrous. That was Chris McManus's view. But we just have a preferred hand to use when we do most things. And we're not alone. There are many animals that do have a preferred side. Horses prefer to run round a track with one leg going is their outer leg compared to the other leg. Some birds prefer to use one particular claw or set of talons to pick apart their prey. Kangaroos and wallabies have a preferred hand to use. Scientists have done experiments watching them in the jungle, in the bush in Australia, to see which hand they prefer to use. So there are lots of species that have a preferred side, but humans seem to be the most extreme, and it's mostly 90% of people are right-handed, and they have been ever since cavemen were wandering around on Earth, because we know this from cave paintings, from studies done in France, that people were painting with one hand and using the other as a template to hold on the cave wall. So it's not a new phenomenon either.
Theo, good morning.
Morning, guys. I just wanted to find out more about Schrodinger's cat experiment and what exactly that has to do with cats.
Right.
Chris.
Okay. Well, the whole thing, this is the sort of uncertainty situation where the thing about quantum mechanics is it's really weird. And Niels Bohr, who is one of the forefathers of quantum mechanics, said, if you're not baffled by this, then you didn't understand it. Because the thing is, when you shrink things down to the very, very small, they begin to behave very unusually. And we think we understand the world on the scale that we are, the size of a human. But when you shrink down to the size of individual atoms and molecules, things don't behave themselves. They behave in a very strange way. And there's a phenomenon called entanglement, where if you can imagine an experiment, say I have an atom, and that atom can issue two photons, one going in one direction and one going in the opposite direction. Now, that atom has made those two particles, but by some strange phenomenon that we don't understand, they become inextricably bound together. So even if they end up on opposite sides of the universe, if I examine one of the photons, I immediately know something about the other photon. And if I change the photon that I can see, I immediately change the behaviour of the other photon on the other side of the universe. So there's something weird that's connecting these entities together, and that's entanglement. Now, the whole thing about Schrodinger's cat is that if you have a cat in a box, until you measure the cat in the box, you don't know if it's alive or dead. So the cat is therefore in both conditions. It's both alive and dead until you look. You don't know. But then when you actually open the box, you seal the fate of the cat. And if the cat has a counterpart which is entangled with it on the other side of the universe, you also change the fate of that cat. Are you confused yet?
I'm suitably baffled, therefore I comprehend.
Therefore you understand. Exactly my point.
Yeah. Julian Stellenbosch, good morning to you.
Good morning. I have a weird question. To Kruger National Park or wherever you have tarred roads, there's a sudden downpour of rain. The road is dry within a few hours, but if an elephant passes and urines on the road, wheeze on the road, then that stain stays there for a long time, even though the dung is dry. Is it the tannins that he eats, the tannins in the leaves or whatever, or why would that be?
Okay, Chris, did you manage to hear that question?
Yes, I did. I'm not a coprologist or someone who's an expert on urine on roads, especially from large pachyderms, but I'll have a go.
Yeah.
I think you're probably heading in the right direction. I mean, there's a range of different things in urine and feces, and so it's possible that they do get onto the road surface. The heat of the road surface then bakes these chemicals and makes them into a very hard, insoluble material, which glues itself onto the road surface. And when the rain comes down, it doesn't actually wash those things away, so you leave a residue there. I suspect that's the reason. You've got things which are poorly soluble and things like tannins, as you say, which are bound up with that, and they probably are not easily washed away. If you were to go along and scrub them and get them away from the road surface with a scrubbing brush, not that you're going to bother doing that in the Kruger Park, something will come and eat you, but then that probably would get rid of them. But I suspect that's the reason, but it's a speculation. If anyone knows better, do please tell me.
Okay, Mark, good morning.
Hello, yes. I need to understand, Chris, how do they manage to measure the distance between, for example, our planet and the star, which is a billion light years away?
How do they measure the distance between stars?
There's a number of ways of doing this. And in the old days, people did this by something called parallax. And you can demonstrate this for yourself, how they did it, very simply. If you hold out your arm in front of you, straight out in front of you, with your thumb pointing outwards like you're trying to be a hitchhiker, and if you close one eye and use your thumb to cover a distant object, and then you open the other eye and close the first eye, you'll see that the object is no longer covered by your thumb. So it appears to have moved. Now, the amount it moves is proportional to how far away your object is. So how do we do this on the scale of the Earth? Well, what astronomers would do is they'd look at a distant object, they'd make a measurement when the Earth was on one side of its orbit, that's like you looking with one eye, and then they would wait till the Earth was on the other side of its orbit and look at the same object, and it would appear to move, and the amount it's moved is proportional to how far away it is. So that's one way of doing it. The other ways of doing this are that we can use what's called stellar candles. An interesting observation made by a lady called Henrietta Leavitt in the late 1800s, early 1900s. She was working at Harvard, and she helped Hubble actually discover that the universe was expanding. She discovered these things called Cepheid variable stars. And what we understand is that different stars of different sizes puff up and shrink at a very predictable rate, and that tells you how big they are. And if you know how big they are, you know how bright they are. And if you know how bright something is, you know that because light spreads out as it comes from the source to us, the further away something is, the brighter or dimmer it is. And so you can use the regularity of the star puffing up and shrinking to work out how big it is, so you know how bright it is, and if you measure the intensity of the light, you can work out how far it is. So when you see distant smudges in the sky, you can use those as stellar yardsticks as well to work out the distance to the stars. So those are two simple ways of doing it.
Excellent stuff. Can we squeeze one in here very quickly? Talma, very quickly, what is your question? Okay, that sounds like the weekend jam right there, Chris, which maybe is a good cue for us to sign off. Thank you so much for sharing your knowledge with us.
It's a pleasure.
We'll do it again next week, of course.
Thanks, Eusebius. Bye-bye, everyone.
Cheers. That was this week's edition of The Naked Scientist.